500 million years ago, there was no sound of birds, no rustle of leaves because there were no leaves, no footsteps on land because nothing had ever walked there. If you stood on the surface of our planet at this moment in time, you would hear only wind moving across bare rock and waves crashing onto shores that no eye had ever seen. And yet, just beneath the surface of the water, something extraordinary was happening. Life was exploding into an astonishing variety of forms, faster and more dramatically than at almost any other point in Earth's 4.5 billion year history. This is the story of a planet that would be almost unrecognizable to us, and the strange alien world of the early Cambrian and Ordovician seas that set the stage for everything that came after. In the next 25 minutes, we are going to rebuild Earth as it existed 500 million years ago. We will map the continents to their true positions, explore the chemistry of the air and oceans, meet the bizarre creatures that ruled the seas, and explain why this single window in time changed the direction of life on Earth forever. By the end, you will understand why scientists consider this era one of the most important chapters in the entire story of our planet. Chapter 1. A world without continents as we know them. To understand Earth 500 million years ago, you first have to let go of the map in your head. There was no Africa in the shape you know, no Americas stretching from pole to pole, no India wedged into Asia. The continents we recognize today did not exist as separate positioned landmasses. Instead, much of Earth's land was gathered into a few large masses drifting across a completely different arrangement of oceans. The dominant landmass of this era was a supercontinent called Gondwana. Gondwana was immense, made up of the crust that would eventually become Africa, South America, Australia, Antarctica, India, and parts of the Middle East, all fused together into a single enormous body of rock. But here is the detail that surprises most people. Gondwana was not sitting where its descendant continents sit today. Much of it was positioned far to the south, with large portions crossing directly over the South Pole. If you could see a satellite image of Earth from this period, the bottom of the planet would not be an isolated frozen cap the way Antarctica is today. Instead, an enormous stretch of solid ground would dominate the polar region, connected to a sprawling landmass that reached up toward the equator. North of Gondwana, smaller continental fragments drifted independently across the ocean. One of these was Laurentia, the ancient core of what would eventually become North America. Laurentia sat much closer to the equator than modern North America does today, rotated at a strange angle compared to its current orientation. Another fragment, called Baltica, would one day form the heart of Scandinavia and Eastern Europe. A third, Siberia, drifted as its own isolated block, entirely separate from the other landmasses, floating in open ocean. Because the continents were arranged so differently, the oceans were arranged differently too. The vast body of water separating these landmasses is known to scientists as the Iapetus Ocean, a proto-Atlantic that would later close and reopen in a completely different configuration to form the Atlantic we know today. Surrounding everything was the Panthalassic Ocean, a single, world-spanning body of water so large it dwarfed anything that exists on Earth now. If you tried to sail from one side of it to the other in a single direction, you could travel for what would have been, in modern terms, tens of thousands of kilometers without ever touching a single scrap of land. This matters enormously for understanding life at the time, because almost every organism alive 500 million years ago lived in the ocean. Land was not empty because life had failed to reach it. Land was empty because, for most of Earth's history up to this point, biology simply had not solved the problem of surviving outside of water. There was no soil. There was no plant life converting rock into nutrient-rich ground. There was no ozone layer thick enough to fully shield the surface from ultraviolet radiation. The continents of 500 million years ago were essentially vast deserts of bare mineral rock, shaped by wind and rain, but completely untouched by biology. Chapter 2: An Alien Sky and a Different Ocean. If you could travel back and stand on one of those barren continents, the first thing you would likely notice is the sky. The sun would have looked slightly dimmer than it does today, because 500 million years ago, our star was several % less luminous than it is now. Stars like our sun slowly brighten over billions of years as their internal fusion processes change. And 500 million years represents only a small slice of that long trajectory. But the difference would have been perceptible. The atmosphere itself told a different story too. Oxygen levels during this period were almost certainly lower than the 21% we breathe today, though scientists debate the exact figures across different phases of the Cambrian and early Ordovician. What is clear is that oxygen had been rising for millions of years before this point, following what geologists call the Great Oxidation Event, roughly 2 billion years earlier. When cyanobacteria first began pumping oxygen into the atmosphere as a byproduct of photosynthesis. By 500 million years ago, oxygen levels were high enough to support the explosion of animal life happening in the oceans, but they had not yet reached modern concentrations. Carbon dioxide levels, meanwhile, were far higher than today, likely several times higher than pre-industrial levels. This created a strong greenhouse effect, and combined with the different arrangement of continents and ocean currents, the overall climate of this era appears to have been considerably warmer than our own, at least for the majority of the Cambrian period. Shallow tropical seas would have been common along the coastlines of Laurentia, Baltica, and the northern edge of Gondwana, creating exactly the kind of warm, sunlit, nutrient-rich water where complex animal life could flourish. The ocean chemistry itself was also different. Calcium carbonate saturation, mineral concentrations, and salinity levels varied from modern oceans in ways that directly shaped the biology of the time. This becomes important when we talk about shells and skeletons, because for most of Earth's earlier history, animals had been almost entirely soft-bodied. The rise of hard mineralized skeletons, shells, and exoskeletons during this period was not a coincidence. It was tied directly to changes in ocean chemistry, rising oxygen, and, most importantly, a dramatic shift in evolutionary pressure that was reshaping life itself. Chapter 3: The Cambrian Explosion. This brings us to the single most important event of this entire era, the Cambrian Explosion. For roughly 3 billion years before this point, life on Earth had existed almost exclusively as single-celled organisms and simple multicellular mats of algae and bacteria. Then, in a geological instant, spanning perhaps only 20 to 25 million years, nearly every major animal body plan that exists today appeared in the fossil record for the first time. Arthropods, mollusks, early relatives of vertebrates, and dozens of other lineages all burst into existence within this narrow window. To put that in perspective, 25 million years sounds long by human standards. But on the geological timescale of a 4.5 billion year old planet, it is closer to a single dramatic afternoon than a slow, gradual process. Before the Cambrian explosion, the fossil record shows us a world of simple forms. jellyfish-like creatures, worm-like organisms, and strange frond-shaped beings from the preceding Ediacaran period whose relationship to modern animals is still debated by scientists. After the Cambrian explosion, the fossil record shows us eyes, legs, shells, claws, and complex predator-prey relationships that would be recognizable in their basic structure to any biologist today. Why did this happen so suddenly? Scientists have proposed several explanations, and the honest answer is that it was likely a combination of factors working together rather than a single cause. Rising oxygen levels made larger, more energy-demanding body plans possible for the first time. The evolution of vision, specifically the appearance of complex eyes, is believed to have triggered an evolutionary arms race, because once one organism could see and hunt effectively, every other organism in its environment faced enormous pressure to evolve defenses, speed, or armor in response. Once hard skeletons and shells appeared, probably first as a defense against predation, they preserved far more easily as fossils than the soft-bodied creatures that came before, which also explains part of why this period looks so dramatic in the fossil record compared to what preceded it. Genetic evidence adds another layer to the story. The underlying genetic toolkit for building complex body plans, things like the Hox genes that control how an embryo organizes its body segments, appears to have evolved somewhat earlier than the explosion itself. This suggests that evolution had, in a sense, been quietly assembling the biological tools needed for complexity over tens of millions of years, and once environmental conditions became favorable, that stored potential was unleashed all at once. Chapter 4. Life in the Cambrian Seas. So what actually lived in these oceans? This is where the story becomes genuinely strange, because many of the creatures that dominated the Cambrian seas do not resemble anything alive today. The most iconic window into this world comes from a fossil deposit in British Columbia, Canada, called the Burgess Shale, along with a similarly important site in China called the Chengjiang biota. These locations preserved not just hard shells and bones, but the soft tissue of ancient animals in extraordinary detail, giving scientists a rare, nearly complete picture of an entire ecosystem frozen in time. Among the most famous residents of this world was Anomalocaris, a creature that would have dominated the Cambrian seas the way a shark or a large predatory fish dominates the ocean today. Anomalocaris could grow to roughly a meter in length, making it a giant compared to almost everything else alive at the time. It had large compound eyes on stalks, a circular mouth lined with plates for crushing prey, and a pair of long, spiny appendages at the front of its body used to grab and hold onto whatever unfortunate creature it was hunting. For decades after its discovery, scientists were so confused by its strange anatomy that different parts of its body were originally classified as 3 separate animals, before researchers realized they all belonged to the same creature. Then there was Opabinia, an animal so strange that when scientists first presented a reconstruction of it at a major conference in the 1970s, the audience reportedly laughed, assuming it must be some kind of joke. Opabinia had 5 eyes mounted on top of its head and a long, flexible proboscis extending from the front of its face, ending in a claw-like grasping structure used to bring food to its mouth. Nothing quite like it exists today, and it remains one of the best examples of just how experimental early animal evolution really was. Trilobites were perhaps the most successful and widespread group of this era. These armoured, segmented arthropods came in an incredible range of shapes and sizes, from creatures smaller than your fingernail to species reaching well over 0.5 meter in length. Trilobites had hard, mineralized exoskeletons, jointed legs, and in many species, sophisticated compound eyes made of calcite crystals. An extraordinary evolutionary solution that allowed them to see using a mineral rather than the soft lens-based eyes most animals use today. Trilobites would go on to survive for nearly 300 million years after this point, becoming one of the longest-lasting and most successful animal lineages in the history of life on Earth, before finally going extinct at the end of the Permian period. Beneath the more mobile predators and scavengers, the seafloor itself was a landscape of strange, stationary life. Sponges formed reef-like structures in some regions, filtering nutrients from the water. Brachiopods, shelled creatures that superficially resemble clams but are only distantly related to them, anchored themselves to the seafloor in vast numbers. Priapulid worms burrowed through the sediment. And drifting above it all were early relatives of jellyfish and comb jellies, pulsing gently through water that had never before supported such a dense and varied community of animal life. Perhaps most significant of all, for us personally, was a small, unassuming creature called Pikaia, along with a related animal named Hycoichthys, discovered in the Chengjiang deposits in China. These small, eel-like creatures possessed something no other animal of this era had: a notochord, a flexible rod of cartilage running along their backs that served as an early precursor to the vertebral column. These humble, easily overlooked animals were among the very first chordates, the group that would eventually give rise to fish, amphibians, reptiles, birds, and every mammal that has ever lived, including us. If you were searching the Cambrian seas for the ancestor of humanity, you would not find a mighty predator. You would find a creature barely a few centimeters long, wriggling through the sediment, easily mistaken for nothing more than food for something larger. Chapter 5: A Silent Land. While the oceans churned with this incredible new diversity of animal life, the continents remained almost entirely silent. This point is worth dwelling on, because it is one of the most striking contrasts between Earth 500 million years ago and Earth today. There were no forests, there was no grass, because grasses would not evolve for hundreds of millions of years. There were no insects crawling across the ground, no animals of any kind walking, crawling, or flying above the water's surface. The land was not necessarily lifeless in the most technical sense, since simple microbial mats and possibly some early lichen-like organisms may have existed on damp surfaces near coastlines, but by any meaningful measure, the continents were barren. This had a profound effect on the physical landscape itself. Without plant roots to hold soil together, without vegetation to slow the flow of water across the land, erosion patterns were completely different from what we see today. Rivers likely behaved in a much more chaotic, braided fashion, spreading across wide floodplains instead of carving the single, meandering channels that plant-covered riverbanks encourage in the modern world. Rain fell onto bare rock and simply washed straight into the sea, carrying sediment and minerals with it, which in turn helped fertilize the shallow coastal waters where so much of Cambrian life was thriving. In a strange way, the very bareness of the land was feeding the explosion of life happening in the ocean just offshore. The complete absence of land life also meant there was no protection against ultraviolet radiation on the surface beyond whatever thin atmospheric shielding existed at the time. Any organism attempting to survive outside of water would have faced a hostile combination of intense radiation, extreme temperature swings between day and night with no vegetation to moderate the climate, and a complete absence of soil or nutrients to sustain complex life. It would take tens of millions of years more before plants finally began the slow colonization of land, and hundreds of millions of years before anything resembling a forest would appear. Chapter 6. Why this moment matters. It is worth stepping back and asking why scientists consider this particular slice of Earth's history so important. The answer lies in the sheer scale of what changed during this window of time. Before the Cambrian Explosion, roughly 3 billion years of evolutionary history had produced mostly simple, soft-bodied organisms. In the space of 20 to 25 million years, nearly every major branch on the animal family tree either appeared for the first time or diversified explosively. Arthropods, mollusks, chordates, echinoderms and more all trace their fundamental body plans back to this era. This period also marks the beginning of complex predator and prey relationships as we understand them today. Before this point, most life forms simply absorbed nutrients from their surroundings or grazed passively on microbial mats. The appearance of active hunting, of eyes evolved specifically to spot prey, of claws and jaws evolved specifically to catch and consume other animals, set off an evolutionary arms race that has never really stopped since. Every predator-prey relationship on Earth today, from a hawk chasing a rabbit to a shark stalking a seal, has its roots in the biological innovations that first appeared in these Cambrian seas. There is also a deeper, more philosophical reason this era matters. When we look at the strange alien creatures of the Burgess Shale and the Chengjiang biota, we are looking at evolution in one of its most experimental phases. A period when countless different body plans were being tested against the pressures of a changing world. Many of these experiments, like Opabinia and Anomalocaris, ultimately went extinct, leaving no direct descendants. Others, like the humble little chordate Pikaia, survived and eventually gave rise to the entire vertebrate lineage, including every fish, bird, reptile and mammal alive today. Understanding this moment in Earth's history is, in a very real sense, understanding the opening chapter of our own origin story. Final words. 500 million years ago, Earth was a planet defined by contrast. Its continents, gathered into strange, unfamiliar shapes and positioned in configurations nothing like the world map we know, were almost entirely barren, silent, and untouched by complex life. Yet, just beneath the surface of its warm, shallow seas, one of the most extraordinary bursts of evolutionary innovation in the history of our planet was unfolding. Strange, five-eyed creatures, armored trilobites, giant swimming predators, and a small, unremarkable ancestor of everything with a backbone were all sharing the same shallow, sunlit waters, working out through billions of individual life and death struggles, which body plans would ultimately shape the future of life on Earth. It is strange to think that the ground beneath your feet was once part of a completely different arrangement of continents, drifting through a world with different oceans, a dimmer sun, and an atmosphere unlike the one you are breathing right now. And yet, if you trace the unbroken thread of ancestry back far enough, back past the dinosaurs, back past the first fish, back past nearly everything familiar, you eventually arrive here in these Cambrian seas, among the trilobites and the strange five-eyed hunters, at the true beginning of the animal story that eventually led to us.